In the last chapter, we studied a section which was entitled Normal Approximation to the Binomial Distribution, and in that section we were concerned with the number of successes R. This section is entitled Sampling Distributions for Proportions, and we're concerned with the proportion of successes R over N, and we're designating it as P hat. Now, the hat business tells us that we're dealing with a sample. This is a proportion in a sample that we're talking about with P hat. So here we were talking about population, here we're talking about sample. That's one difference. Another difference is the business of R, the concern with R in that previous section, and the concern here with R over N. But there are some striking similarities. For example, the notation that we're using in this section is very similar to the notation from before. N is the number of binomial trials, R is the number of successes, P, the probability of success on each trial, Q, the probability of failure on each trial, which is calculated as 1 minus P. Now, in that previous section, we said that if NP is greater than 5 and NQ is greater than 5, then our distribution that we are studying is relatively normal. And we can say pretty much the same thing here, that if these conditions hold, then the p-hat distribution is relatively normal and can be approximated by a normal random variable x, with the mean of the p-hat distribution is p, and the standard deviation of the p-hat distribution is this. Now, we'll get back to these calculations in a little bit, and they're different because because of central limit, because of our emphasis on R over N rather than just R. But as I say, we'll get back to this in a bit. Now, this idea of going from a distribution which is discrete, it's discrete because there are a fixed number, N is a fixed number, to a continuous variable, X, caused us before to have to do a little correction here when we made our calculations. Let me refresh your memory. Now, recall that we saw histograms that looked something like this. And on this axis, we have the probability of R number of successes. And here are those numbers of successes. And each number is associated with a little histogram bar, and that histogram bar has to do with the probability of that number of successes, and so on. Okay. Now, in that study, we often had a situation where we would say, gee, I wonder what the probability of having anywhere from 2 to 5 successes would be. And so we would want the area that is associated with the shaded region here. Now, in making that calculation and in transferring that to the idea of X goes from some number to some number, we did this. We said, gee, rather than go from 2 to 5, we want to collect all of the area under here. So, gee, we need to go actually from this shoulder of this histogram, from this value all the way over to that value, right in between the 5 and the 6. So we thought of it like this. We said, well, we're going to take the 2 and we're going to subtract 0.5. You see, to arrive at this value. And over here, on this side, we're going to take 5 and we're going to add 0.5. Well, in our study here in this section, it's related here to this idea, because all we're doing, we're thinking of this as the probability of R over N, you see, and this is going to be R over N, and all of these R's are going to be over N. You see, that's the idea. And so that idea transfers all the way up to our continuity correction. Everything was over N. It's this 2 over N, you see. We're going to subtract 0.5 over N. And over here, this is the 5 over N. And we're going to add 0.5 over N. So the continuity correction is 0.5 over N. We're subtracting it on one side and adding it on the other side. Now, let's concern ourselves with continuity correction in this next problem. It says, suppose N equals 25, and we have a p-hat interval from an R of 10 to R of 15. That is, 10 successes to 15 successes in this distribution. We want to convert this to an X interval. Now, let's begin by thinking about p-hat is R over N, And when r is 10, you know, n is 25, so it'd be 10 over 25 or 0.40. When r is 15, p hat is 15 over 25 or 0.60. Now we want to think about our continuity correlation factor. Now this p hat interval is from 0.40 to 0.60, but we need to take into account this continuity factor, this correction. All right, the continuity correction factor is calculated as 0.5 over n, and n in this case is 25, so the continuity correction is 0.02. So we have to subtract that from the left side and add it to the right side when we convert from p hat to x. So the p hat interval is from 0.40 to 0.60. The x interval is from 0.40 minus the correction to 0.60 plus the correction. So it's an x interval of 0.38 to 0.62. I think it's important to point out here that the amount of this continuity correction factor, the amount of that is going to change according to n. And in fact, if n is really big, you know, we're changing the denominator here, so if n gets really, really large, then this fraction becomes relatively small, and in fact it could be relatively negligible if n is sufficiently large. So as n gets bigger and bigger and bigger, this factor plays a smaller and smaller role. Consider this problem. Healthy adult bone marrow contains about 56.5% neutrophils, which is a particular type of white blood cell. However, if this level is significantly reduced, it may be an early indicator of leukemia. And the reference for that information is given. The A part of the problem says, in a laboratory biopsy, a field of n equals 50 bone marrow cells are observed under a microscope. A special dye is inserted, which only the neutrophils absorb. Then the number R of neutrophils in the field is counted. Although the field size n equals 50 is fixed, the number of neutrophils R is a random variable, so the proportion p hat equals R over n is also a random variable. Explain why p hat can be approximated by a normal random variable, and then what are the mean and standard deviation for the p hat distribution. Well, let's answer the question about why p hat can be approximated by a normal random variable first. You know, we've looked at this situation before, and it has to do with the value of NP and NQ. Now, in our problem, we know that N is 50, P is 0.565, and Q is 1 minus P, or 0.435. So we can easily calculate NP and NQ and see that they're both greater than 5. Now, what about the mean and standard deviation for the p hat distribution? Well, we have formulas for those. The formula for the mean of the p hat distribution is rather trivial. It's simply p, and p is 0.565. Now, for the standard deviation, we have a little calculating to do. It's the square root of pq over n. We have the information about p, q, and n, though, so we just pop that in and make the calculation that the standard deviation is 0.0701. Now, the B part. Suppose Jan had a bone marrow biopsy and p hat was observed to be 0.53. Assuming nothing is wrong, that is, there's no leukemia, what is the probability of getting a biopsy this low or lower? That is, compute the probability that p hat is less than or equal to 0.53. Now, the process of computing the probability that p hat is less than or equal to 0.53 involves several steps. We have to change this to a probability involving x, and then we have to change that to a probability involving z. So we're going to go from the idea of p hat to x to z. Now, when we go from the p hat idea to the x idea, that's where the continuity correction comes in. So the first thing we're going to do is make the calculation of continuity correction, and it's 0.5 over n. N in this case is 50, so the continuity correction is 0.01. Now that allows us to, now remember we were adding that on the right side and subtracting it on the left. Well, we only have a right side situation here where we have to do some adding. So we add the 0.01 to the 0.53, and now we can change this into a probability involving x. So the probability that p hat is less than or equal to 0.53 is the same thing as the probability that x is less than or equal to 0.54. Now we need to change the x into a z, and remember that that just involved a little relationship that z is equal to x minus the mean over the standard deviation. And here we know that x is 0.54, and we know the mean and standard deviation. We pop the information in, and we find that the z value is negative 0.36. Now we want to find the probability that z is less than or equal to a negative 0.36. We use the table, and we find the probability to be 0.3594. Now, take a look at the C part. Now, we're going to interpret this in just a little bit, but let's go to the C part first. We have a very similar situation, and we're going to march through it in much the same way. It says, suppose Meredith had a bone marrow biopsy, and p hat was observed to be 0.41. Assuming nothing is wrong, that is, there's no leukemia, what is the probability of getting a biopsy this low or lower? That is, compute the probability that p hat is less than or equal to 0.41. Now the calculation is much the same as it was before. I invite you to pause the tape or stop the tape here and make the calculation on your own and then come back and roll the tape. But let's run through it right quick. The probability that p hat is less than or equal to 0.41 needs to be, we need to change it into the x idea and then to the z idea. We need the continuity correction again, and it's 0.01 as it was before. So we're going to add that to the 0.41, and we are converting therefore into an x probability. So it's the probability that x is less than or equal to 0.42. Now we change the x of 0.42 into a z value, and we do that by using the same relationship that we did before, and we find that the z value is negative 2.07. So we're finding the probability that z is less than or equal to negative 2.07. We use the table to find that value to be 0.0192. Now, here's where the interpretation comes in. Consider item D. It says, based on the probability estimates in parts B and C, which do you think is the more serious case, Jan or Meredith? Explain. Well, let's recall the probabilities associated with these two studies. Remember, Jan had a probability associated with p hat of being less than or equal to 0.53 of 0.3594, and Meredith had a probability that p hat is less than or equal to 0.41 of 0.0192. Now, the idea is that we're assuming that both of these are healthy ladies, and we are computing the probability that a healthy person would have a reading of the type that is given here. And it turns out that the probability that Meredith would have such a low reading is very low, that it would be very unusual that a healthy person would have a reading that is so low. So that's the idea here. And therefore, Meredith is the more serious case. In a previous chapter, we talked about control charts, and we're going to revisit that topic here in this section. I think it's important for us to review just a little bit what we talked about at that time, though, because many of those ideas are going to prevail here. Now, we found that control charts were a way to kind of dynamically or continually evaluate whether or not a mean, which has been established from historical information, is being maintained. That is, are we drifting above or below? Is our mean changing over time due to some circumstance? A good example, I think, is in order here for us to bring this to mind. Remember, we talked about a situation involving a large hotel out west, and this hotel was evaluating the situation involving housekeeping, where every day they attempt to prepare rooms for their guests by 3:30 in the afternoon. Well, they take information about the number of rooms that are unprepared at 3:30. And the mean, let's say, and I'm just using something convenient here, let's say that the number is 17. And as I say, it's a large hotel and they use a lot of part-time employees, so the number can fluctuate quite a bit, and they just want to kind of maintain control over that amount. Well, all right, so let's say it's 17. Now, they want to establish a control chart, and a control chart, remember, contains this information basically. The mean from historical information is established, and then you create markings for the mean plus 2 standard deviations and the mean plus 3 standard deviations on the top side, and the mean minus 2 and minus 3 standard deviations on the bottom side. We're going to chart information, and the information is charted on a day-to-day or week-to-week or month-to-month basis, and for the hotel it was charted on a daily basis. Now, so the days are listed down at the bottom here, and we need some value associated with the mean and the standard deviations and all of that kind of business. So over here I'll just use the 17 as I mentioned, and this area of our control chart is some number of rooms left unprepared by 3:30 in the afternoon. All right, so that's the idea. So it's some number of rooms. Now, if the standard deviation, let me just take something easy here. Let's say it's just one room is the standard deviation. Then the mean plus 2 standard deviations would be 17 plus 2, or 19. The mean plus 3 would be 20. The mean minus 2 would be 15, and the mean minus 3 would be 14. All right, so that's the idea. That's the layout. And then, so all of this information now is from historical data. And what we're doing is we're charting a situation from this time forward in order to see if this mean may be drifting in one direction or the other. So that was the idea. And every day the number of rooms that are unprepared by 3:30 can be charted. And on this day maybe it's 16. And on this day maybe it's 17. And on this day maybe it's 15. You see, and so we can actually go through and chart and make dots for each one of these. And then we talked before about what it means for this information to fall beyond 2 or 3 standard deviations. And that allows us to decide whether or not this information is in control or not. And we have out of control signals that we talked about. Let's talk about those now in review. Now, in this section, by the way, the control charts are going to be referred to as P-charts, but our out-of-control signals are the same as they were before. Out-of-control signal number 1 is that 1 point falls beyond 3 standard deviations on either side. Number 2, a run of 9 consecutive points on one side of the center line or the other. And number 3, at least 2 of 3 consecutive points lie beyond 2 standard deviations on the same side of the center line. So let's have a look at a problem and see if we have any of the out-of-control signals. Lee is a cadet at the Honolulu Police Academy. He was asked to make a P-chart for reported minor property crimes. Lee chose a small neighborhood with 92 families. Each family is viewed as a binomial trial. Success means the family was a victim of at least 1 minor property crime in the past 3 months. Police reports gave the following data for the past 12 quarters, or 4 years. Assume the 92 families lived in the neighborhood all 4 years. Now just take a quick look at the chart information here. Notice the numbers for each quarter going from 1 through 12. We have the number of so-called successes. Kind of a dubious definition of success, isn't it, to be the victim of a crime? But at any rate, the number of successes is given for each of the quarters. And the p-hat calculation, the R over 92. Remember, 92 families. The calculation of the 0.12, for example, in the first quarter is made by taking 11 and dividing by 92. So 11 over 92 is 0.12. All right, so that's how the information is derived. Now, what are we going to do with this? Well, we're going to make the p-chart, and in order to make the p-chart, we need some idea of mean and standard deviation. And the mean and standard deviation that we're talking about has to do with the entire study. All of the information has to kind of be brought together to give us the mean and standard deviation for the overall period of time. So what we're going to do is add the number of successes. We're just going to add, for example, in the first quarter there were 11, in the second quarter there were 14, in the third quarter there were 18, and so on. So add all of those to get the total number for R. Now, what about the number of trials? Well, gee, there were 92 trials in every quarter. So we would have to multiply the 92 times the 12 quarters. Well, here's what I'm talking about. Here's what we do. We think about the number of trials each quarter is 92, and the number of trials, the total number of trials in 12 quarters would be 12 times 92, or 1104. Now, the total number of successes is 206. And at this point, we can calculate a proportion of successes for the entire time period. Now, we're going to call this P bar because we are using pooled information here. And this is not we can't exactly call it P because this is not a mean number associated with all neighborhoods. It's just this particular neighborhood. So P bar because it's pooled information. All right, so it's the total number of successes over the total number of trials. So it would be 206 over 1104. So P bar then is 0.1866. And then Q bar can easily be calculated. It's 1 minus P bar. It's 0.8134. Now, the mean, we know for a P hat distribution is equal to P. But we don't have P, but we do have P bar. So we're going to approximate the mean using P bar, and it's 0.1866. All right, now standard deviation. Well, the standard deviation, we have a formula, and it's PQ over, it's the square root of PQ over N. We don't have P and Q, but we have P bar Q bar. So we're going to approximate our standard deviation using those values. And popping those into our formula, we find that the standard deviation is 0.0406. All right, now we might take a moment to make the calculation of P bar, which is the mean, and add 2 standard deviations, subtract 2 standard deviations from that. Take the P bar and add 3 standard deviations, subtract 3 standard deviations. Those are the levels for our chart. So let's take a look at the chart now. Now let's just kind of go all around the chart and study it just for a moment. On the right side, we have those levels that I was just referring to, where we would need to make the calculations for P bar plus and minus 2 standard deviations, P bar plus and minus 3 standard deviations. That's how those levels were calculated. Now on the left side we have proportions, and those are just for reference for placing the information into the chart. Down at the bottom we have each of the quarters are listed. It goes from quarter 1 through 12 quarters. Okay, and now all we need to do is read the P hat information from the charts and put a designation, put a value or an X or something into the chart to designate each of those. And so away we go. We put those into the chart, and we have our P chart. And now we look for out-of-control signals. Well, we can pretty easily see, I think, from this P chart that we don't have any of the out-of-control signals. We would be looking for out-of-control signal number 1. 1 point falls beyond 3 standard deviations on either side. Well, no, we don't have that here. A run of 9 consecutive points on one side of the center line. No, we don't have that either. We have 4 on one side of the center line, but we don't have 9. And the third out-of-control signal would be at least 2 of 3 consecutive points lie beyond 2 standard deviations on the same side of the center line. No, we don't have that either. So we have none of the out-of-control signals, so this information is in control.